Okay, so this is the third webinar of Galaxia. If you've seen the other two webinars, I'll just go over what previous ones were and what about this one's going to be. The first webinar, I talked about the basics of Java, about how you code normal Java. The second webinar, I talked about the electronics and the phone UI of FTC, all the modern robotics, the Rev Expansion Hub, how they connect, a couple of things that you need to know for the programming itself. And in this webinar, we're going to be talking about the programming in Android Studio for the competition. So, hold on. Okay, first thing you're going to do, this is a bit more the physical aspects. You're going to need to install the SDK from GitHub. Basically, first the organization made this group of classes that you could use to write your code, and they made it easier to do. So you simply also have to go to the Android Studio site, download it. Fairly simple. Okay, don't mind that, it's just working here. Okay, so next thing you need to do is to import the SDK into Android Studio so that you could see all the classes. Okay, now a little bit more about the code itself. When you open the SDK, you'll see two folders, FTC Robot Controller and Team Code. Now, all of the code you're going to write will be in Team Code, all of your classes. FTC Robot Controller holds templates that you could copy from to write your own code on top of them. So, I don't have a specific example, but let's say FTC Robot Controller holds a template for writing an autonomous code. And then what you need to do is copy that file from FTC Robot Controller to Team Code, rename it to something that your team will understand, and then use that to code write on top of that specific code for your year's competition. There's a lot of useful things in there. You could check it yourself. There's how to control color sensors, linear, a bunch of things that I'll explain later on. Okay, now for the very basics, there are two types of classes that you could use. There's linear and iterative. Both can be used for the same purposes, but they're just structured differently. Mostly, if you want it to be a little bit cleaner, you use iterative for teleop and linear for autonomous. Autonomous and teleop, I'm sure you already know, but I'll go over it. Teleop basically is those 2 minutes and 15 seconds that the driver can control the robot, and autonomous are the 15 seconds that you can drive on your own, that you have to let the robot run through pre-existing code. So I'll show you why you use iterative for teleop. Okay, this is how iterative code looks, sort of. Now, this is a class that I copied over from the FTC Robot Controller. The code looks like this. It starts off with this line, that basically the first line, public class, basic op mode. This is basically the name of the specific file. Then you have this first segment over here. Over here, you define all your variables. And then after you define all your variables, you have 4 functions. In these 4 functions, you put in all of your code. Okay, so I'll just talk about what these 4 functions do. You have the first function, init. Init everything that's under init will run once the moment someone pressed on the init button on the phone, on the robot controller. Basically, in the first segment of the iterative code, here you define all of your motors. Here you define values, things like setting all the arms inward so that they don't go out of the frame perimeter. Over here is the setup of the actual game. You also have initialize loop, which you don't really use. It's the loop that happens while you press on initialize. Then you have the third function, start, which is a function that runs once the moment you press on the green arrow, the moment the announcer yells go. And then you have loop, which is going to run in loops until someone hits the stop button on the phone. And over here you have all the code that you need to repeat itself. So basically you could settle this down into segments. So depending on what type of code you want to do, you put it in a different function. It's very simple and easy. You also have a code for stop, which we specifically didn't use last year. But it's for things like stopping the robot after the game is done, things like that. So iterative is pretty easy to understand because it's very block-like formation. You have the first block for variable, the second block for initialize, third for initialize loop, and so on and so on. In this example that I show on screen, you could see a line of code that the moment the person presses start, the robot drives around based on the controllers themselves in a loop. So the other type of file you could use is linear. Now, linear acts more like the Java programs that we showed you until now. Functions that work from top to bottom, one after the other. Basically, it does the first line and then the second, and so on and so on and so on until the bottom. For this one, it's things you're already used to doing. How you wrote classes in Java, how you write classes in C, they work the same way over here. Now that's why also people like writing in linear autonomous, because you do one function and then the next and then the next, and it's very easy and very it's easy to understand. And iterative is easier if you want to have multiple segments like you do on the teleop. Okay, so two specific things about the linear that aren't in teleop. Instead of having init loop, start loop, you have two functions. These two functions basically wait for start. The moment you write wait for start, the program will stop working until someone presses the stop button. It's sort of like a delay or a wait for in Java. Then instead of having a function called start loop, they have a Boolean that the code returns true if you are in the off mode. I personally liked this more last year because it felt more like Java, but the two of them are interchangeable. You could use any one you want. Okay, autonomous versus teleop. I already sort of explained this before, but I'll go over it again. Autonomous is the 15-second period that you can control in advance, and teleop is the period that you have to control with the Xbox controllers. Now, just to show you how it looks on the phone itself that I showed yesterday, here you've got the two arrows. So if you choose something to be written down as teleop, it will appear on the right segment of the phone, and if you choose something to be autonomous, it will be on the left segment of the phone. So you can organize your code better. Also over here, you could see the initialize button that I was talking about. That you press initialize, and then it runs one code, and then you press it again, and it'll press play. Now, one more thing about this that I didn't say before. A little bit more about the lines of codes. I talked a second ago about how the code is written and how it functions, the order. Now I'll try to talk more about the functions themselves that you use in the code. The first 2 and 3 that you'll see are @teleop, @disabled, and @override. @teleop is the easiest to explain. You do @teleop like it's written down here, and then you write in the name of the specific class, what you want it to show down on the phone, and what group of classes it works as. For example, if you want to have it more organized on your phone, like we did, and have like autonomous 1, autonomous blue, autonomous red, that's what you write down in this part up here. Now, @disabled is what you usually see right under it. It's the default that will appear there. @disabled prevents it from appearing on the phone. This is so that if you have a lot of lines, if you have a lot of different programs and you don't want all of them appearing at the competition, you disable some of them so that it would be more clean. All the temporary ones you made. The third one, you shouldn't touch this, unlike the other 2, is @override. This one just appears over all the 4 functions, all the 5 functions, telling you that those are functions of the code and that you shouldn't touch them. Okay, now I'm going to talk about more about the specific lines of code. This is more like we used in the Java. You have here the variables, the local variables that this code is going to specifically use. For example, you have the DC motors the code is going to use. Sometimes you have things like encoder positions. One example that we see over here is a class called elapsed time that the code uses. Elapsed time, what it does, it's basically a timer. It tells you the amount of seconds that have passed since the last reset you did to it. For example, you could do elapsed time and then they named it runtime. And then over here what they did is they did runtime.reset so that it would be 0 at this moment. And then you could do things like runtime.seconds, and it will tell you the amount of seconds that you have. This is personally used for things like autonomous, if you want to find out how much time you have till the end of the autonomous, and just for checking things in general. Now, other lines that we have here, telemetry, which I think I might have elaborated later, but I'll say now. Until now in Java, you have print screen. Here you have something that's pretty similar, but it has its own differences. It's called telemetry. What you do is you do add data, the type of data, and then the specific data either you want to write down. And after that, you do update. Basically, instead of printing it down on the log like we did in Java, this code will write down it on the phone, that's on the driver station. You could use this for, like I said in the first webinar, if you want to see what's wrong with your code, it's generally good to print as much as possible. Like you see over here where they print the values of the motors, if the robot's running or not. It's good to give your drivers a lot of feedback about what's going on. Okay, so the next thing we have here are DC motors, how you control them. Now, DC motors are a little bit more complicated. What you do is there is a class called DC motor. Okay, so it works like a number, like in object-oriented programming, where it has its own value and it has its own set of functions that you could use. So, and specifically to DC motors, you create the DC motor, give it a name, give it a value, The value is basically what motor is it. And then you could use a bunch of functions to control it. Okay, so in this example, which is a teleop, you have left motor and right motor. What you do here is you start off by, usually this is what you do with all of the code. You define the motors in the beginning as your local variables, and then in the initialize, you set them to this line of code. Basically, last webinar or in some of the explanation papers, you had to do that config and then giving the motor a specific name. So this is that very same name. You do hardware map dot get, and then you put the type of motor, the type of value, for this case DC motor, and then you write down the name that you wrote down on the phone when you did config. So in this example, it was written down on the phone left drive and right drive. So in the initialize, it defines the motors, and then what it does is it does this function. This function, it just sets the direction that the motor would spin. Then other things, other things you could do with a motor, for example, is set power. Set power is a function specifically to DC motors where you give it a value, a speed from -1 to 1, and then the motor will spin at that speed. So for example, if you have a lift mechanism that pulls a rope, you do set power 0.5, and then the motor will spin at 0.5 speed. Motors only work at doubles. You have to put in doubles that are only from -1 or 1. If it's bigger than 1 or less than -1, the code will just give you an error. Other lines that you could see specifically here, like I said, was the runtime resets, the wait for start, the while off mode is active. Also, what you have here is range. Range, basically what you do is you just, let's say I have a value that's any number, but I only want it to be between two numbers. So let's say if I have 17, but I only want it to be between 0 and 10, it will round it down to the maximum. So the code used this, for example, because they didn't want left power to be greater than 1 or less than -1. So they did range clip, and then they put the value between the two of them. It's specific things that they have in the SDK, a lot of tools that first built in advance so that you don't have to do all these things yourself, to simplify and make the code look more aesthetic. Okay, so the next thing I'm going to talk about is hardware maps. Hardware maps, it's a very good way of writing your code. You don't have to use it. Basically, what you did until now was to define the motors every single time you created a new function. You had to do DC motor is equals to hardware map in every single class you did. This isn't efficient because if you have, let's say, if you want to change the name of the motor, now you have to go and change it in every single class you made. So instead of that, you could do something a lot simpler. This is also in the FTC folder. You create the motors only once, and then every time you want to use this class, you do hardware pushBot.initialize. And that's basically, you could do this. You could do all of the setting only once, and then not have to worry about it later on if there's like a conflict in one of your lines. This, I specifically copied hardware pushBot. Really, when you're starting off with Android Studio, just go through all of the example codes. That's the best piece of advice I can give you. Just see whatever there is over there. There's a lot of useful examples like this one. Here I have the actual explanation about hardware map. Starting off with things like creating the motor, and then doing, you could also store here things like variables. Let's say, what value should the motor be when driving forwards? So you do, inside another function that's pre-made, you do public void init. You do this line of code. These two you simply copy. And then in all the rest, you do as if you were to do it in an actual in an actual class. Okay, so DC motors and tank driving. I'll talk a little bit more about this. This is a specific code that we used last year. I explained most of this, so I'm just going to show the example itself. Here, instead of doing here's an example of what we did. We created a hardware pushbot robot. This is how hardware pushbot looks. And then you do the name that you created, .init. Then we did, this is a specific example of a robot that drives using the Xbox controllers. But I'll talk a little bit more about them later, so I'll just continue. Okay. Up until now, I showed you things like driving to a specific distance using the speeds of the motors. Let's say if you want to drive forward, you do speed 1. But that's not really useful if you want to do autonomous. If you want to use autonomous and you want to have to drive specific paths, like driving forwards and turning and angles, there is a class that in the FTC robot controller called Auto DriveBy Encoder. This thing, basically what it does all the calculations for you. Basically, hold on, I have the actual code here. Basically, what you do here, this is an autonomous code that's linear. You start off with defining your hardware. Then you go to specific variables that change for every robot. These you change specifically to your code. This is just a template. And then you have this function. They already made the function for you. All you need to know is to know how to use it, basically. So I'll explain one by one what these do. It starts off with 4 or 5 variables. Each of these, I'll start off with the 2 basic ones. You set as a variable, for example, what you want your maximum speed to be. If I want it not to go over a certain speed, what your maximum turn speed will be, what the diameter is you know what diameter is. It's what's the diameter of the wheels, what's the gear reduction, what's the counts. 3 of these are more technical terms. You learn more in mechanics. But basically, when your motor spins, it doesn't directly explain how much your robot drives forwards. On the robot are connected encoders. How encoders work are when the robot's wheel does a full circle, it gives a certain amount of extra numbers to a variable. So in this example, in the default of Andy Mark, 1 rotation of a wheel will raise the encoder value by 1,440. A simple encoder is one that works that 1 rotation on the wheel, the encoder goes up by 360. It's an easier way to think about it. Basically, what you have to do in this class, you just copy it to the team code file, and then you change the variables to things that are specific to your robot. For example, the gear reduction of the motors. If you have a gear reduction, they're usually written on the motor itself. Then you have the diameter of the wheels. And these are also specific to every single team. So what this does is it basically does all the calculating for you. And all you need to do is use this command, Encoder Drive, and then you put in 4 variables. You put in the speed you want to drive, how much your left wheel is going to move, how much your right wheel is going to move, and a default timeout in case it doesn't manage. So I'll try to explain this with an example. Let's say you have a class that needs to drive 20 centimeters forwards, turn around itself, and then drive 10 centimeters. So you do Encoder Drive 0.5, which is your speed, and then you say how much the left wheel is going to have to drive, how much the right wheel is going to have to drive, and a timer, a specific amount of time, that if that time passes, don't continue trying to go to that distance. For example, if your robot only did 15 centimeters and it got stuck in a wall, it's going to continue trying forever to get to those 20 centimeters. The default timeout can help you if you have problems on the way. The specific how this function works is a little more complicated. You could read into it. I could explain it lightly, but you don't need to understand how it works, because you could just use the function itself. So I'll explain it lightly. It starts off with checking if the op mode is active. So basically, if you didn't press play and you by accidentally used Encoder Drive, the wheels won't turn if the match didn't start yet and the guy didn't whistle. Then what it does, it creates 2 variables. It gets this is a function if you want to get the position of the motors, like what rotation they are in. So it basically says, okay, my left motor is in 50 degrees, my right motor is in 75 degrees. I want my left one to go 50 degrees plus 2 meters, and my right one to go 75 plus 2 meters. And then you have more preset functions that basically automatically drive to those positions. And then you have things like runtime reset. It's just a while loop that checks if it exceeded the amount of time. Okay. Next, I'm going to talk about servos. Servos, not about smart servos though. Servos, they are very different from motors because servos don't spin continuously. They have a specific amount of degrees that they can turn. Most servos work that they can only turn 180 degrees. That's the ones that you get in the main package. So instead of setting the speed that the servo rotates, you set the position that the servo would be. So like DC motors, you create them by doing new servo. You do like servo with a capital S, and then you give it a specific name. And then all you have to do is, instead of set speed, you do set position. Now set position only works on doubles as well, from 0 to 1, sometimes from -1 to 1. Also that you could check in the AndyMark site what the specifications are. But usually it starts off 0 and then turns 180 degrees to 1. So in this example, it did if it sets the left claw to one specific side, the right claw to another specific side, and then it drives forwards in a loop. Okay, so next I'm going to talk about color sensors. Color sensors are another thing that you use a lot, especially this year, I think, in FTC. Basically, it's like a servo, it's like a DC motor. You have to create a new one, and they have a specific amount of functions that you could use with them. For example, so most of what you're used to until now is how colors work. It's RGB, right? It works on cameras, it works in printers, where it tells you the amount of red, the amount of green, the amount of blue, and then you could find out the exact color. But when you're doing programming, that's pretty hard to program. You can't, if you want to get a specific color, it's hard to program the range that the color exists on. So that's why people created HSV. RGB works on red, green, blue. HSV works on hue, saturation, value. So if you were to imagine an RGB cube where you have all the available colors, you'd have, like, if you have maximum blue, maximum red, you'd have pink, maximum green, and maximum red, you'd have, and no blue, you'd have yellow. So instead of working like a cube, HSV works on a pie or a cone. Basically what this does is, instead of getting red value, green value, blue value, you have H, which is the hue, which is the color of the specific thing that you see. For example, it goes in a circle from blue to pink to red to yellow. You have saturation, which is how strong the color is, and value, which is how strong the value is. Now, this is a lot easier to program than with RGB, because in RGB you'd have to have a very not logical program to do. It would be very complicated. And with HSV, let's say if I want a specific color, let's say if I want to see the color red, instead of having to specify the RGB that I like, all I have to say is the range of the hue of the angle, the minimum strength I would want to get, and the minimum value that I would like to get. It simplifies the code a lot more. Here is another example that I copied over. You do normalized color sensor, which is like defining a DC motor, and then you create the new one. Yeah, okay. So then what you do is, hold on, sorry. What you do is instead of doing color sensor, the color sensor that you can connect, you could ask what the HSV is, or you could do color sensor dot get color, and then it will return to you if it's white, if it's red, if it's blue. It's sort of like how the FLL works with the Lego, where you have a color sensor and then it would tell you what color. Hold on. It gave me a little error. Can you still hear me? Okay. So this is a lot simpler to use, and it's a lot more compact and shorter to write. You also have, like in the Lego, you have enable light, you have value, you have range. The most prominent thing that you'll probably use is simply get color. Let's move on to, hold on. I'll go back to this in a second. Xbox controller code. Okay, so you have to read the two Xbox controllers. The code also has a very easy way to do this. You already have defined, you don't have to define them like all the other things. You have two gamepads, the two ones you're allowed to connect to the phone. In the code, they're simply called gamepad 1, gamepad 2. So, for example, I want to see if someone's pressing the A button. There is a Boolean gamepad.a. The Boolean is being updated separately. So if I check, let's say for example, if gamepad1.a is true, then the robot drives forwards, and I do that in a loop. The moment I press A, it will do the function in the if statement. So there's three types of Booleans, which are basically buttons. You have 3 or 4 actually. You have the 4 buttons over here, A, B, C, D. They're written just gamepad1.a, gamepad1.b, gamepad2.b. Then you have the right bumper and the left bumper. If you played with an Xbox, this is pretty self-explanatory. Basically, the right bumper are the top buttons. You press on it, and it's just like an A button. It'll just tell you if it's pressed or not. Then you have the 4 D-pads, which is this plus right over here. So let's say if you press down on this one, then the Boolean D-pad down will be true. There's also a 4th one, which is, let's say, a 4th and 5th. The start button and the select button, if you want to use them, are also buttons. And pressing down on the joystick is also a button. Now, later on, I'll explain how you can see the full list. There's a full list on the internet, on a specific site that first made, I think. I'm not sure. Then you have Booleans, which are simply pressed or not pressed. And then you have the more complicated ones, which are, let's say, if you want to get the value of the joysticks. If you want to get the value of the joysticks, it won't give you yes or no. It will give you a value, like you'd expect. You'd have, let's say, gamepad dot, and then the which stick you're going to use, left stick or right stick, and then the axis you want to use. Let's say x-axis from left to right, or y-axis from up to down. This will return to you, on default, all the joysticks are on 0, and then all the way up or all the way right would be 1, and all the way left and all the way down will be -1. So, an example that we used last year is, for example, these 3 simple motors, left wheel, right wheel, and an arm. So, I said that the left wheel will be the forwards and backwards value of the left stick. The right wheel will be the forwards and backwards value of the right stick. And then you'd have an if statement. So basically, if I move the left joystick up, the robot will turn, moving the left wheel forwards. Then if I move the right wheel up, it will move with the robot turning left. So, and then let's say another example. I said if I press on the A button, move the arm to the 1 position, and if I press on the B button, move the arm to the 0 position. Another type, you probably won't use them, are the triggers, the sticks on the back. They work from, because the triggers aren't like yes or no. There's a specific amount that they get pressed. So you have to check what the value is. So for example, the right stick, the triggers give you a value from 0 to 1 about how pressed they are. For example, our code last year, we did that if you press the right stick all the way, it would drive forwards at 1 speed. So we would get the strength of how much you pressed and then convert that to driving forwards or backwards. Okay, so, right, it's not, 1 second. Okay. Next thing I'm going to explain about is JavaDoc. Now, JavaDoc is a site that you could see the link to on the bottom right. This site holds a lot of information about every single class that I talked about until now. This is how it looks. You have the information itself in the middle, and then you have the list of every single class that you need on the left. Here's an example. You could see over here DC motor, which is, we're just going to go and show an example. Okay, so if there's still things, specific things that I didn't explain about now, you could go over to the site, press Control F, and then find that specific thing that you need, and there will be an explanation, a very detailed explanation about how that works. For example, the DC motor that we talked about just a second ago, you press on it, and then it will show you the list of all the functions that it has, the list of all the values that it has, how you define it, things like that. So, for example, you have the ones that I already showed, which were set power, set target, get power, get position, and then you have the more complicated things like is busy. You can see the full list over here. And hold on. If there's things you still don't understand, things like distance sensor, how they work, you could just go to the site. Hold on, I'll actually show you how the site looks. Hold on. You go to, just search JavaDoc FTC, and you press on the first link. Here you go. Here you could see everything, all the classes that are documented over here. For example, gamepad. You could see here all of the values that the gamepad holds that I talked about, the A button, the B button, the type of value, Boolean, you have here the ID, the start button, the joystick accesses. This is another tip that really helped us last year. It's really important to use sites whenever you have a problem. The two things, if you have something that you don't understand, are to go see if there's a template existing in the FTC robot code, and to go to this site and see if there's explanation about that thing that you want to know. There is all types of things. I'll show you another one that I didn't talk about. For example, I'll just find a good example real quick. No, gyro sensor they stopped using. One second. Here, op mode. Here you can see all the values that you can get in op mode. The get runtime, init loop, initialize. Basically, I show this link. I'll send it later to Gabriela so that she can send it to you. It's a very useful site, and we used it a lot personally. Are there any questions? No? Okay, I'm pretty much done. I think I covered everything. Yes? So if there's any questions, you can write them down now, or you could send them to my mail later on. I'll send my mail to Gabriela so she can talk to you guys. Oh, here's one question. How can we use an auxiliary class within our autonomous class? Auxiliary, if I'm not wrong, is the camera that you guys are using this year, right? The camera of the phone, right? Hold on, I'll just check it out real quick. The name sounds pretty familiar. You can create a second class and use its methods in the autonomous class. Yes, you could. One example of it working is the hardware map that I showed you. You could create an abstract class and then import it. Actually, you could do it fairly easily. What you do basically, if you want to create a class and then import from it things, you create a class, make sure it's in the same directory as the autonomous class that you're talking about, and then you simply do import in the top, and then you write down the name of the class like you'd use a DC motor, and then you press dot, and you'll see a list of all the available functions that you created. Basically, for what specific uses do you have? If you want to create like a specific function, or how do we compile the, how do you compile the code on Android? Yeah, I forgot to mention that. What you do is you connect the phone, you connect the phone to the computer with a USB, the phone that is connected to the robot, the one that has the white screen on it, and then in Android Studio, you have a green button on the top, a green arrow, right arrow. I don't have a specific photo of it, but you press the green right arrow, and then it'll ask you to compile it. It'll tell you if it's looking at the right phone. You press OK and yes. Then you wait 30 to 40 seconds, and you'll see a little bar on the bottom right showing that it's being downloaded. Any more questions? Specifically, I think there's an error that's with Android Studio about uploading your code to the phone. This is something that happened to our team, 11567. What happened was the version of Android Studio was 2.3, and the phone's version was 3.0. So every time they try to upload the code, it would erase all the files. There is a workaround that you could do. It's or to update the Android Studio, or to move the file onto the phone, and then you could compile it from the phone itself using onbot Java. It's this little extension that you have under the configure robot. Hold on. Do you recommend, next question, do you recommend us to move the robot to the parking zone using fixed distances or by sensors? Okay, this is a more specific question to the competition. From previous years, the robot sensors, like the robot's fixed distances, are pretty accurate. You could rely on them. That's what we did last year when we had to go to the beacons and press them all. So sensors are harder to program, but you could say they're more reliable. The thing is, at little distances like the size of your map, you could use the fixed distances, and they would be pretty accurate. What won't be accurate would be the starting position before the robot moved forwards. So you might want to use sensors for aligning your robot to a wall, things like that. In general, it is smarter to use sensors because they are harder to program, but they are generally a lot more reliable. And using only fixed distances, it doesn't always work because sometimes they build the maps bigger than how it is in your place where you tested it. And what happened to us is we started changing the numbers while the competition was going on. So using sensors is a bit nicer for if you want consistency. But you could also use the encoders. But I would say that it might be a little bit better to use the sensors. It also depends how accurate the sensors would be while using them. Let's say a color sensor to see a stripe on the floor might be even less accurate because you don't know the angle you're going to hit the stripe. You have to try to think of a sensor that would be very accurate, and try not to use the gyro of the Lego because it's faulty, for example. How many autonomous modes do you recommend us to use? Generally, as much as that you could still keep track of. We had at least 8 autonomous codes. Most of them didn't work, but it's generally good because the thing is, the game is super dynamic, especially in your year. And the fact that it's dynamic, that it's changing, like that there's different teams, means that each team will be different from the last one. And you can't guarantee yourself that every single team will align their programs to what you're doing. So having a lot of, something that we started doing now, and we recommend, that some of our teammates recommended not to do, is to fix yourself only on one position. Let's say only to do one task on the map, and only creating one autonomous code. That's generally not smart, because if you have another robot that is the same thing, that only has one autonomous code, you have a problem. It's generally better to, if you have a robot that's specifically designed for something, you should put most of your effort into the autonomous that it's designed for, but you should also have a couple backup autonomouses for, let's say, if you're working with a robot that is better at that specific function. Like if you have a robot that's better at putting the blocks into the relic lines, that's faster at doing it, then you should create an autonomous that it does something else. Or if you have a robot that's better at climbing. Or in our competition, if you have a robot that's better at putting things at the scale, you should create backup. You should focus on making autonomous for what you want, like a central one that you're gonna want to use. But it's good to have backups always. So that means that we should make different autonomous modes for every position that we get. Yes and no. You could create autonomous codes for every single position. You definitely could. but it's not that smart. I wouldn't recommend it unless it's necessary, because what if you have to do a quick change on one, then you have to do it for all four. What we did on our code, because we have in FRC this year, we have the two sides of the switch. Instead of creating 16 autonomous codes, we're planning on doing 7. And basically having like, I don't know if you could specifically do that on yours. I think the arrow only lets you. It's better to create all your program designed for blue, and then once you're done and you like it, you copy it and then you mirror it for the other position. But if you meant for every single position that we get, as in like the positions of the robot, you should create multiple positions. But if you, specifically in the FTC, yes, you need to create one for red, one for blue, because it's flipped sometimes. For every starting position, okay. How do you connect the gamepad to the phone? I talked about that more in the last webinar, but I'll say it again. You have two Xbox controllers or two Logitech controllers with USBs, and then you have two pieces that you need to buy. One of them, I don't have the photos here, sorry, but you need to have a USB piece that takes multiple USBs and merges them into one. And you need to have a USB piece that's an OTG. Some software stores can know what that means. OTG takes the USB and converts it to the phone connection, which is Type, which is the mini USB. So those are the two things you need. You need an OTG so that you can connect the USB to the phone, and you need the splitter that takes multiple USBs and puts them into one. The phone should automatically recognize them. If it doesn't, you could try to press all the buttons on the start button to make sure if it's on. But generally, you could see if it's on once you see that glowing white controller on the top right. Where I write the program, another question. Where I write the program in the team code or in the robot controller. Yeah, I said that in the beginning. The team code is where you put all your code under team code, Java, and then org first inspires FTC Team Israel. Where you see the README file, that's where the program will read all of your code. That's where you have to do it. Hold on, I'll just maximize it. FTC robot controller, you don't touch, you don't delete or add things to it. It's purely made so that you can see no, not purely made. It's made so that you could take the examples from it. Are there any more questions? Hold on, some more things that. Oh yeah, I remember now. You can't make an autonomous that has variables. So you do need to make autonomous codes for every single position you'll get. You need to create one for the different teams that you're going to be, and for the different positions the robot will be at. Okay. I'm sort of done. Thank you very much for listening. If you have any more questions and you forgot and you want to tell me, Gabriella will send you my Gmail. I'll answer them. My personal Gmail, where you could ask me anything. Hold on, let me just, there you go. Thank you very much. I'll just turn off the microphone real quick. You're welcome.